Okay, so thank you all for coming to today's talk. First of all, I guess we'll mention, welcome, 2 new additions to the group. So Arna Bhattacharjee, the second Bhattacharjee in the group, is starting his PhD. We'll be here for 3 years at least anyway, so welcome. And Laurent Contier is coming. You'll be here for 2 years or something, more or less. So yeah, welcome guys. We're happy to have you. And now for this week's talk, we have Sophie Emma Mikkelsen, who's going to be here as well from September, the 3rd edition to the group. And she's here visiting us for 2 weeks, and she will give a talk on split extensions and KK equivalents for quantum projective spaces.
Yeah, thanks for the introduction. Yeah, and thanks for the opportunity to come and visit you here. I'm really looking forward for my longer stay in September. Yeah, so in this talk, I will talk about some joint work with Francesca Ricci on constructing an explicit KK-equivalence for quantum projective spaces and the commutative systematic class Cn+1. So let me give you the plan of the talk. So first, I will describe for you the Waxman and Soppelmann quantum sphere. Is Q2 and +1, from which we can define these quantum complex projective spaces denoted CP. So here I will describe them as graph system algebras. Which is due to Hung and Szymanski. So they both describe Waxman and Soppelmann's quantum sphere as a graph system algebra, and from that we can describe these quantum projective spaces as graph system algebras. Then we will look at an exact sequence. We have the compact operators. We have C of CPQN and C of CPQN. And this exact sequence here becomes crucial in finding the explicit KK-equivalence, which we want to do. Then the second thing I want to do is just to define KK-equivalence for you. Not in that many details, but I will give you the definition, and then we will look more closely at it at the seminar on Thursday. And here we will also see how to construct an explicit KK-equivalence when we have split exact sequences. And then as the last thing, I will show you a construction of splitting of this exact sequence. And for the last part here, it becomes crucial that we can describe these quantum spaces as graph system algebras. So we tried to see if we could find such a splitting before we consider them as graph system algebras, but here it becomes much more clear if you actually look at the graph system algebraic picture. Okay. So first thing, this quantum symplectic sphere by Waxman and Soppelmann, I denoted by C of SQ Cn+1, the system algebra of this symplectic sphere. So it is, sorry, not the symplectic sphere. I've been working too much with symplectic sphere. Just the quantum sphere. Yeah, so it's the universal. Generated by some elements at 0 plus n, satisfying some relations. So first we have that set I, set j equals q, set j, set I, when I is greater than j. For the joint, we have that set I star set j equals q set j set I star. When j and q are not, I are not the same. Yeah, maybe I should go over here. So now when I and j are the same, we have that set I star set I is the same as set I star plus 1 minus q squared. And then we sum over all j's greater than I. Set j star. And then we have the sphere relation, which justified that we call it a sphere. So we have this. If we take the sum over all set I star, get 1. Here, no, they can not be the same. But so they just have to be different. And if they are the same, you have this relation here.
Oh yeah, sorry. Yeah.
Okay.
Yeah.
Okay. Yeah. See? Yeah, and these relations comes from the fact that this SQ so 1 plus 1 is defined as the.
Sorry, just a question in the chat.
Yeah.
It's already
Sorry. Okay. It's a Q always. Yeah. Okay. So these relations come from the fact that these quantum spheres are defined as this quantum homogeneous space for SUQ, the SUQ group. Yeah. And also note that in the case where Q equals 1, C of SQ is 1 plus 1. It's just the continuous function on the sphere. So we are back to the classical case. Yeah, maybe I should also mention that I look at Q between C1 1. Yeah. Okay, so now since we have defined this as a universal system algebra, we also have an U of 1 action on it. So there exists this U of 1 action on C of SQ plus 1, which maps the generator set I just to W set I, an element in the circle. And it follows that this is an action by universality. Okay. Just write it in. Because then I can define the quantum, these complex quantum projective spaces. So they are given by taking the fixed point algebra under this action. And it's also possible here to define it as a, to describe it as a system algebra with some generators and relations. And then you look at the generators, Pij, set I, star, set j, plus relations which you get from the relation on the sphere. I don't want to write them out, but it is possible. Okay. Yeah, so as I said, I want to present the description of these two spaces as graph system algebras. So let me first call some things on the graph system algebras, and I will also give you the definition. So if we take a directed graph, so we have here the set of vertices. And the set of edges, and then we have the range map telling you where an edge ends and the source map where it begins. Then we say that a vertex it is called regular if we have that. If we have this set here consisting of all the edges with V as its source, if this is finite, so this consists of all the edges such that the source of V. So if it's finite and non-empty, then it's called regular. We call it a sink. If the source inverse of V is if it's empty, meaning so you have no outgoing edges, and then we call it an infinite emitter. If it emits infinitely many edges, as the name says. Okay. Yeah.
Does the action on the quantum sphere have a particular property, for example, outerness?
Okay, so if we have a directed graph, then the graph sister algebra, sister of E, is the universal sister algebra. Generated by two sets. So the first is a set of projections, which are indexed by the vertices in the graph. And another set of some partial isometries, which are indexed by edges in the graph. Okay. Yeah, but okay. Yeah, it makes a lot of noise. Okay, they are a bit small, but it's fine. Yeah, otherwise they are in colors, so not like yeah. Let's try. I will try with this one. Yeah. Okay. Yeah, okay, that's good. Okay, so and then they have to satisfy some relations. So first we have that all these projections, they are mutually orthogonal. The partial isometries have orthogonal ranges. Yeah, and then we have the next three relations, which are known as the Kreuzer-Krüger relations. So first, if we take the projection SE star, SE, then we get the projection corresponding to the range of E. If we take the projection SE, SE star, then we get the projection corresponding to the source. Sorry, then this is a projection, but it's less than the projection corresponding to the source of E. And last condition, if we now take the sum over all SE, SE star, such that the source of E equals V, then we get the projection P. Ah, okay. How does a relation? What a question. Why does a relation? It means so it means here that you have that this is a subprojection of this projection here, and so you see they are also. But if you sum over all of them, then you get. Yeah. Okay. Yeah. If you want, that's of course. Yeah. Exactly. Yeah. And then these are known as the integral relations. And I should also say here that we need, for the last one, we need V to be regular. Otherwise, we don't have a finite sum here. Okay. Okay, so now let's look. Yeah.
So, hence in particular, if you consider the next star, you get a principle of U1 comodular from the principle U1 rather dense since there are space. Not exactly dense, but it's still true.
Okay, it's okay.
This is true.
Yeah. Okay, good. Okay, so now let me give you the description of this quantum sphere as a graph system algebra. So okay, so this is isomorphic to a graph system algebra, which we denote by L2n plus 1. And this is due to Hang and Szymanski. Yeah, so they have this paper where they both look at they look at various of these quantum spaces, and in particular at these quantum spheres and also quantum complex vector spaces. Yeah, so let me tell you what this graph is. So L2n plus 1 has vertices. And you gave me this. Yeah. It has vertices which we denote by V1 to Vn plus 1. And it just, which we denote by Eij. And here we have that I greater than or equal to 1, less than or equal to j, and then it goes to n plus 1, such that the source of Eij is just Vi, and the range of Eij equals Vd. So, for example, if we look at L7, so when n equals 3, then we have a graph like this. So we have 4 vertices. Since we have all the edges Ei, we will have a loop attached to each of them. And then we have that they are all connected by a an edge, but only going in this direction. So we have edges like this, all the way here, and okay. So also note that by proving that these spheres, they are isomorphic to this graph system algebra here, we also obtain that they are actually all isomorphic because the Q's does not show, it does not show up in the graph system algebra. So we know that C of SQ is 1 plus 1. They are all isomorphic for Q, and then we can actually include 0 also. So Huygens and Szymanski also proved that if you take Q to be 0, you'll still get the same graph. Okay. Yeah.
Because I mean, you've got 0 multipliers and.
Yeah, so you have. Yeah, exactly. Yeah. Yeah, but yeah.
So then all the generators commute, so it really gets in the community.
No, if you have 1.
No, it's 0.
Yeah. Oh, sorry. If you have 1, then you get that they all commute.
Then IJ equals 0.
Hmm?
Isn't this one here?
Yeah.
That relation.
Then you still have
Q's.
Is this an explicit isomorphism?
yeah. I wanted to say something. Yeah, it's okay. Yeah, that was the next thing. So it's they give an explicit isomorphism, but
Then IJ, but they don't. Then I comes IJ 0.
Then J times I might not be 0.
Yeah.
because then you cannot take the inverse. Yeah, so that's exactly. Okay, so sometimes you also write the relation and then other way around. Of course, then you have the inverse. But yeah. Okay, but yeah, it is an explicit isomorphism. So yeah, I don't want to erase that one. So what they do is to find some representations. So from C of SQ to N+1 to bounded operators on L2 of N plus Z. And the same for the graph system. And then they compose them because they are faithful representations. So by crossing with the Z, they make them into a faithful representation. And then if you compose them, you get this explicit isomorphism, but it still involves some analytic argument. You have to analyze the spectrum, and it involves some infinite sums in it. Yeah. Okay, so I don't want to write it here, but it is explicit. Yeah. Okay. And since we have this explicit isomorphism, we can also see how the U of one action translate into this graph system picture. So, which we need when we want to look at CPQN as a graph system graph. So we know that this is by definition C of SQ plus 1. This fixed point algebra here. And we know that this is isomorphic to the graph system algebra of L So n plus 1. And then I need to specify what the u of an action is. And this u of an action here turns out to be the gauge action on the graph system algebra. So it means that we have this. We have a gauge action. Gamma on any graph system algebra. And it maps the projections just to themselves and the partial isometries. Here you multiply by the element in the setting. Okay, and looking at this explicit isomorphism, we see that this action here is precisely the gauge action. Okay. And now it can be shown that this fixed point algebra here is itself a graph system algebra. And it's isomorphic to the graph system algebra of a graph Fn. And this Fn here, it has again these n plus 1 vertices. We denote them by W1, Wn plus 1. And then we have infinitely many edges from Wi to Wj if I is less than j, countably infinitely many edges. So for example, if we have F3, so we have 4 vertices, and then we would have something like this. Where I denote by this means that we have countably infinitely many of them. So just to give you an idea of where this, how you get this isomorphism here, it can be shown that a graph system algebra, you can see this as the closed span of all S alpha, S beta star, where alpha and beta are some finite paths. So these infinitely many edges comes from looking at paths in this graph here, where you get some elements here that are of course preserved under the gauge action. So that's why you get these infinitely many of them, and you don't have any loops, because if you just take, you cannot, if you take this path here, you don't get an element in the fixed point algebra. So that's the idea. Yeah.
Say that the graph, I'm going to have a dense polynomial generated by
Yeah.
But also a dense polynomial that is written inside CPN or spherical construction, but these are not the same. They're not preserved in very small under the isomer. They're two different.
Yeah.
Well, you would want the projection.
Yeah.
Yeah,
Exactly. Yeah, and also when you look at the isomorphism, it's clear that it works on only at the sister algebraic level. Yeah, exactly. Okay. Okay, so now let's take a short look at the K theory and the ideal structure, and then I will move on to KK theory. So So knowing that this graph system diagram makes it very easy to compute the K-theory. So if you have a graph, just any graph system algebra, then we look at a map KE from this 3 billion group of degenerators given by these regular vertices, all regular vertices. So all the vertices in the graph, and it takes KE of V, and then we take the sum over the range of E for all E such that the source of E equals V minus V. Yeah. So you can use this formula for any system algebras, and if you have some finite graph, then you can also look at the adjacency matrix and look at the co-kernel and the kernel, because now the K0 of the system algebra is isomorphic to the co-kernel of this map, and K1 is isomorphic to the kernel. For these quantum complex projective spaces, this is very easily computed because we don't have any regular vertices, so this is just the zero map. So we obtain that K0 of C of CP is isomorphic to Z plus 1, and K1 so I don't remember it, but at some point I looked at this order. So someone have been looking at this order, but you don't get it precisely from
I guess
this.
all times are purely infinite anyway. So
Yeah,
order
yeah.
structure is kind of degenerate.
Yeah,
but-
yeah, yeah. Okay. Yeah. So we know the K-theory, and then let me say a few words about the ideal structure, because then I can show you how we get this exact sequence.
This is for this app.
Yeah. Okay. So yeah. So here we have this system of. Yeah. So I'm using this, but I mean that we look at the graph system.
Everything is infinite.
Yeah. Okay. Yeah. Okay. I didn't wrote. So they are all infinite emitter, and except this one, this is a sink.
Yeah.
Yeah. Okay. Yeah. No infinite emitters and no sinks. Yeah. All vertices. Yeah. And maybe I wrote 0 below. Oh, I'm sorry about that. Yeah. But there's just all of them. So here you get. Okay. So just a few words about the deal structure. So if we have a subset of the vertex set, then we can define an ideal, which is just the ideal generated by all PV H. So close two-sided ideal in the graph system algebra. And then if we put some condition on this H, we get all ideals which are gauge invariant. So in the case where of
Question in the chat, sorry.
Yeah.
Ali is asking, can one naively encode something which is related to the Kunz semigroup of C star E from this map KE.
Oh, I'm not sure what the consumer group. What? Yeah.
Tends to feel.
Yeah, or yeah.
Or
No, I don't know, but there is a condition about seeing n moves of Taylor and Klein, and then you have an injective mark from deal where you actually go into it and I just tell you that this moves in there. But I don't remember how to say a graph in the condition about the C.
Yeah, I don't remember that. No. Yeah.
I have a question.
Yeah.
That's a really ideal of graph system algebra and then graph system algebra.
If the ideal is,
Like I waves that you find
Hmm?
is it possible graph system algebra?
so
I mean, can you use some?
yeah, so if you so I will also come to it in a moment, but if you look at the quotient, then you can describe it as a graph system algebra. But the ideal here can be described as all. You can write it as a closed span of all these as alpha as beta stars. So you don't get immediately that it is a graph system algebra itself.
You cannot just take some age and elaborate it to the vertices that you consider.
And then get a graph system algebra. But okay, so I'm not aware of if there's some condition where you know always that you get a graph system algebra. I'm not sure about that.
But in general,
Not what I know of. No. So in this case here, we will see that if I look at a particular one, we would get the space of compact operators. Yeah. Okay. Yeah. Okay. So if we assume that, let me just see. Okay. So there is this theorem by Bates, Pask, Rayburn, and Szymanski saying that IH is gauge invariant. And we have this one-to-one correspondence between these subsets being hereditary and saturated. And it means that, so hereditary it means that if you have an edge here between a V and a W, and you have that V lies in H, then W should also be in H. And saturated it means that if you take a W which is regular, so not a sink, not an infinite emitter, and you have all the edges with W as its source lies inside H, then W should also be in H. And then you know that for what is called row finite graphs, this is a one-to-one correspondence. And row finite means that you, let me just, yeah, so V is either regular or sink, so it cannot be an infinite emitter. Yeah. Okay, but if you have something which is not row finite, which is the case here, it's still possible that you still get that this is gauge invariant if H satisfies these two conditions, but it's not sufficient. You need something else. But in our case, since we don't have any loops, we actually get that this is still would still be a gauge invariant ideal if we look at H corresponding to this vertex here. Yeah. I think I need to speed up it up. So if we take H BB. Okay, let me also mention that in the non-row finite case, this has also been solved out. So here we also have a complete description of all the gauge invariant ideals, but it is a bit more complicated. And you can also describe the quotient as a graph system algebra in this case. Okay, but if we let H be equal to V and V is a sink, then it can be shown that this ideal is isomorphic to the space of compact operators on a separable Hilbert space. It comes from the fact that you can construct a set of matrix units inside it by looking at all S alpha, S beta, where alpha and beta are some paths in the graph, and then they should have range equals to V. And then you get this one. Okay, so in our case, we have the sink W1 plus 1. So we have H equal W1 plus 1. And from this, we get that the C-star algebra of Fn, motion by IH, will be isomorphic to the graph C-star algebra of Fn minus 1. By this more general theory, where the idea is that you remove all, you remove the vertices here, and then you remove everything going inside that vertex, and then you get precisely that the quotient is isomorphic to this. Okay, and from this we get an exact sequence. Okay, start of Fn. And in the case where we have CPQ1, we have the complex numbers here. And then, of course, we know that there exists a splitting. But the question is now, if we have a splitting here and how to construct it. And that's what is essential for our construction of this explicit KK equivalence. So I can give you some more detail on this later if you want. Yeah. So let's move to the second part on KK equivalence. So let me just recall for you a few things about KK theory, but I think it is fresh in our minds from the seminar. But if we take two sister algebras, then we can form this abelian group, which generalizes the K theory and also the K homology. So if we have KK of CB, then this is just K0 of B, and all the way around get the K homology. And that's also a way to generalize the K1 group. Okay. So let me now give you the definition of KK equivalence. So we say that A and B, if we have two sister algebras, which should be separable, then A and B are KK equivalent. Arrive as A B. That's KK. If there exists an element X inside KK of AB, and another element Y inside KK of such that if we take X tensor, X, taking the Kasparov product with X and Y, then we get 1 on KK. Yeah, and if we take the product the other way around, we get 1 on KK. Yeah, and if we have such a KK equivalence, then the KK classes will always be the same for the C-style class. They are also always isomorphic, and you can write this isomorphism explicitly using these 2 classes here.
The same, it doesn't imply this is a stronger condition. Maybe.
If you have that all the KK classes are the same.
Will you get an X and a Y like this?
If all of them, as a yes, so if you, I'm actually not sure. Yeah, I'm actually not sure. Yeah, if you have that all the KK classes are the same for those two, if you then get and then you get those 2 elements a KK equivalence.
This is in one of if you have this.
Arbitrary number one. I suppose between them as a reading, would you automatically get these elements? It's somehow like a very strong version, I suppose.
What?
Of the group. Also,
I mean, it should be the KK.
so yeah, so you have that KK of A. Yeah, C is always isomorphic to KK of B, C, and the other way around for all several system algebras. If you have KK equivalence, then you know that the K theories are always the same. And then the question was the other way around. Yeah. Exactly. Yeah. I will go more into details with this on in the seminar first. Okay. Yeah. So now the question is, so why is C of C n actually KK equivalent to Cn plus 1, and also so it's commutative. So I said that we want to construct an explicit one, but we already know that this explicit KK equivalence already exists. So we can argue in 2 different ways. So the first is due to a theorem by Rosenberg. And check. So it says that if we have 2 separable sister algebras in what is called the UCT class, I will not explain this further, but it means that they satisfy what is called the universal coefficient theorem. But if these conditions are satisfied, and we have that the K theory of A is isomorphic to the one for B. Both K0 and K1, then A is KK equivalent to B. So you can determine if they are KK equivalent just by looking at the K theory. And in our case, we have, let me write this down. So we have this exact C. So what did you say? Yeah, and what does it?
And do you need to assume that the K doesn't have K here is a portion or something like that?
I think you can always look.
Yeah. Yeah. I think this should be okay. Yeah.
Also, doesn't this answer the question?
Yeah, why they are. Yeah, precisely. Yeah. So because I'll just write this. So if you have Q1. So all commutative system algebras, they are contained in the UCT class. We also have that the space of compact operators is in the UCT class, and then the UCT class is closed under taking extensions. So if two system algebras in the extension is in the UCT class, then the last one is also. So we get that this one is also in the UCT class. And then, of course, by induction on N, and using these exact sequences here, we get that all CPQNs are contained in the UCT class. And I already computed the K theory, and I also raised it again, but the K theory for CPQN is Zn plus 1. And we know that the K theory here is also Zn plus 1, and we can also compute it to be the same for the commutative counterpart. So by this result, we get that they are indeed KK equivalent. Let me just, without writing it down, say that we could. There's also a the next I wanted to say is a result due to Nashville and to Z, where they looked at some quantum versions of some homogeneous spaces for some specific groups, specific Lie groups, and then they proved that all of these more general quantum homogeneous spaces, that they are KK equivalent to the commutative counterpart. And in particular, CPQN falls also into this, since we can write C of CPQN as C of SUQN plus 1 UQN. I think I get it right with this. And then it follows directly by that result that they are also KK equivalent. But we don't get an explicit one by any of these results here. Yeah, and that was our goal, to construct this explicit isomorphism. And let me say that right now we have this explicit isomorphism here, but we still don't know how to find an explicit one between the commutative system algebra and Cn plus 1, and then we could compose them. So this is still, it's still a question how to find an explicit one here. Okay, yeah, but now let me explain to you what this KK equivalence has to do with these split exact sequences. So let me call it this fact. So what I will say now is stated as an exercise in the book by Blackadar, but it says that if we have here a split exact sequence, just by J, and then we have Q, and we have a splitting S, then so a split exact sequence of system algebras, then we get that E is KK equivalent to J plus by using the element J, the class of this star homomorphism J, which lies inside KK of JE, and the class of S, which lies inside KK of BE. So here we get an element in KK of J plus B. E. And then there's a way to construct an inverse for this element here. And then we would obtain that this is a, this gives us a KK equivalence. Yeah. So we started 5 minutes. Right. Yeah, so I can consider it. Okay, but I think I will, if you're okay now, I will explain the inverse for you in the seminar on Thursday. But you can find an element in E, J plus B such that you get precisely this condition. Okay, and here you also see where the splitting appears, and it also appears in the inverse. Okay. So now, if this exact sequence here, if it splits, then we have an explicit KK-equivalence. Between C of CP QN and K plus C of CP QN minus 1. And then the idea is that you can compose all these classes you get, such taking some direct sums, because now we know here, of course, that this is also, we can also find an explicit KK equivalence between this and K plus n minus 2 and so on. So in the end, you will get an explicit KK equivalence between CPQN and K n times plus Z. Yeah, and then compose them. And that I don't want to write this explicitly. It's a bit long, but it's possible. And then you can use that K, the space of compact operators is KK equivalent to the complex numbers. I also think that you actually gave. We saw that K is explicit KK equivalence last time. Yeah. So it all boils down to having this splitting of this exact sequence. Okay, and I will show you how the splitting looks, because it's actually not that complicated when you look at these graphs as algebras. So we need to look at CPQN and CPQ n minus 1, and then I have to call the vertices and edges by some different names in the corresponding graphs. So over here we say that we have vertices W I goes from 1 to n plus 1. Here we have VI from I from 1 to n, because we have n minus 1. And here I denote the edges by Fij m, where m indicates that we have countably infinitely many of them. Oh, sorry. And here I denote them by E, I, J. Yeah. Okay, so now I can give you splitting. So we have this map from the graph system algebra of Fn to the graph system algebra of Fn minus 1. And we just have to say, of course, where are all these projections and partial symmetries mapped to. So if we take P, let's see, Wi, it's just mapped to P Vi if I is not n plus 1. Oh, sorry, I should go the other way. Yeah. That's why it didn't make sense. Yeah, of course, sorry. Yeah, so Vi is just mapped to Wi if I is not n. Okay, so we don't, but we have to do something else with the last vertex. So here we have PVN, which we map to PWN plus PWN plus 1. For the partial isometries, here I didn't, but yeah, so EIJM, it's just mapped to SFIJM if J is not n. So if it does not go into this last vertex, and then we do something similar as here. So we take SE IJ n, and then we map it to SE I SF I n plus SF I n plus 1. Yeah. And then it's not that difficult to show that this is actually a yeah. So it's not difficult to see that this is actually a splitting. Okay, I erased, of course, these defining relations for the graph system algebra, but remember that the last relation of the Kunz relations, here you need to assume that the vertex is regular. But in this case, we don't have any regular vertices, so we don't have to look at that relation. And that's actually crucial. So if you want to do something, if you try to do something similar with the quantum spheres, it fails because of that last relations. So somehow we are able to construct this splitting. Yeah, since we don't have this last relation here. Yeah. Okay, and then as I said, we can compose all these equivalence classes and get an explicit KK equivalence between CPQN and CN plus 1. So let me just say a few words of what my motivation was. So my motivation comes from non-commutative bundles. So here there have been a description of some non-commutative sphere bundles where you have base space and fibers, which are quantum complex projective spaces. And then what I would like to investigate is if we could describe an explicit KK equivalence of the total space, which is a flag manifold, using this explicit KK equivalence coming from the base and the fiber. So, and again, we know that this total space is also a KK equivalent to its commutative counterpart by this resolved by Nesterov and Toussaint. But another thing to look at is also what is called weighted projective spaces. So here you have the action defining these weighted projective spaces. Instead of having ZI mapped to WZI, you have ZI mapped to some WMI ZI. So have some weights showing up. But here it's not, here we still need to describe them all as graph system, which has not been solved out yet. But we know that a splitting should exist because of some UCT argument again. You can also find that in our paper, but that's actually why we realized that we should be able to find a splitting here, because by some UCT argument, we can show that it should exist. And that's the same for some weighted projective spaces. Yeah. Yeah, I think that was everything. Thanks.
some point when you said that the ideal generated by a sink is the compact operator, but the graph that you had with infinitely many edges. So if you have the sink, like the point before, all the sources of this point go to someone in H. So it should be in H also. And by transition, I feel like this should be the whole graph.
So if you have, so it was if you, okay, maybe
I think I understand wrong what is saturated, but
if you have an edge going inside here, W, and this one here is an H, then this here should also be an H.
yeah, but if W is in,
If this is an H, then we don't need to have this one being an H. It's
so
the other way
what
around.
is saturated?
Saturated, but saturated is only true if you have regular vertices. It's,
Okay.
so you only have to assume saturated for regular vertices.
Okay,
But that's
because
right. Otherwise, because here it says that if you have
all the ranges that are
ends
in
up in-
H,
exactly,
then
then
the
it's-
one before is in
exactly,
H.
yeah.
Okay,
but since we have infinitely many ones, we don't have to.
okay. Thanks.
So does, excuse me, does the UCT answer this question up above? So if all the KK, if these, I guess the other way around. So if you knew that KKCA was KKCB,
Yeah.
then for all C, then take C to be the complex numbers. This tells you in particular that the
Yeah,
K
okay, yeah.
things.
Yeah, that's right.
For all C, then is it obvious to take C to be A and then get that back up and identity the group B by the isomorphism?
Hmm. Yeah, yeah.
I guess, yeah.
Yeah, yeah. Yeah, yeah,
Yeah.
yeah.
Okay, and so did you say for the quantum spheres, you don't get a splitting?
Yeah, so you cannot do something similar as here to get a splitting. Yeah, and then but I'm not sure about that. I cannot explain you the argument, but we were explained that at the in the classical case you cannot have a splitting for the spheres, and therefore you cannot have it for the CPQ, the CPN. So actually you don't. This is actually some quantum. You only see that the level of the sister algebras for these quantum complex vector spaces. Yeah. But the weighted projective spaces here, the graphs we know they looks like something like this, where you still have infinitely many edges between all of them. So here, yeah, maybe it should still be possible to find it, but we don't. We only know the graphs is algebra picture when you start with SQ3. So when you only have two generators, and then you just have that the quotient is the complex numbers. But so yeah.
Thanks. So just one question. In the case of n equals 2, do you have a fighting chance of being able to sort of pull everything back and consider this split exact sequence in sort of geometric terms, in terms of the original Q-deformed spheres?
So you mean, yeah.
So maybe you'll have a funny isomorphic copy of the compacts, but otherwise realize the surjection of the two sphere onto the one of the CP2 and Q onto CP1Q in like sort of geometric terms, and realize the splitting sort of in terms of the Q-deformed spheres as well.
Yeah.
You're asking in terms of the generators, U by J.
Yeah, in terms of the generators, yeah. If
There's no natural, I mean.
or is this all really fundamentally a creature of this sort of graph theoretic picture?
So the splitting we have here.
Yeah.
Yes.
Yeah.
Maybe. Sorry, I'm not sure I understand.
No, so you constructed the split exact sequence.
Yeah.
Using this graph, sort of Caesar algebra picture.
Yeah.
I'm just wondering if, even if only in the case n equals 2, you can sort of pull everything back using the isomorphisms to the literal
to the
Q-deformed
spheres.
complex projective spaces.
Yeah.
And see what that looks like, or if it looks like anything reasonable.
Yeah. So if you try to take this splitting we have here and do something similar for the spheres, that's your question for the quantum spheres.
No, rather, if you take the split exact sequence, sorry, I'm a mistake. If you take the split exact sequence you have, which is constructed in terms of this graph Caesar algebraic construction, and you pull everything back using the isomorphisms with the literal CP2Q and CP1Q, let's say, and rewrite everything in those terms. I mean, do you have a fighting chance of getting anything like nice in terms of the usual generators and relations for those quantum projective spaces? Like, can you write the split exact sequence in terms of directly?
Can you write them in terms of the z's basically?
Yeah, exactly.
So you've defined everything in terms of the z's at the start is still there. Can you write this splitting in terms of the algebraic generators?
Yeah. So you know the isomorphism. So if you mean just writing it in terms of these generators, looking at them as generated by these Zi star Zj. But so I haven't done it, but you know the explicit isomorphism between.
Sure.
So it should be possible, but I haven't worked that out.
You should just cut off the last of the first set of the generators, and that will map subjectively onto CPN minus 1, and there's an obvious splitting, whether it's implied.
So you're saying what mapping?
I mean, there's kind of an obvious guess for what these maps should be on the generators by J.
Yeah. So what is the obvious?
Just renumbering. I mean, the relations that you have in the CPN when step down, I mean, they have the same relation. Extra generators put on, so when you just map those back to the generators. No, I mean it's an interesting question.
Yeah, of course. Okay. Yeah.
But then the thing is that accept more flags, so without actually having that.
Yeah, of course. I see. Yeah, it's a good question. Yeah. So the reason why we went to the graph systematic picture was because we find it hard to see what the splitting should be, because it's essentially because you have that you take this your sum. If you take the sum over all these Zi star, then you get 1. But if you just so that was our problem, because it should be preserved, of course. But it's a good question. So it could be interesting to see what is this using this explicit isomorphism, which is known. So that's why we went to
We've had enough, plenty of them over the course of the hour and a half. Okay, then we thank Sophie again for a very nice talk. Okay, we got to cut this off.